You are currently the only person in this conference.
I remember to.
We always forget. Okay, so welcome to this second lecture on materials. Last time on Friday we saw everything about soft magnetic materials, and now we will move to hard magnetic materials. But before starting with hard magnetic materials, I would like to go through what we learned last time. So of course you're welcome as every time to write in the chat your answers. So what is the difference between soft and hard magnetic materials? Somebody who is courageous enough to answer to this very difficult question. I know Monday morning is not the right moment. Okay, let's go on. So, of course, the main difference is coercivity. We speak about permanently magnetized materials, which are the hard magnetic materials, and temporarily magnetized materials. What are eddy currents and what is their role in applications of soft magnetic materials? So eddy currents, everybody knows that from electromagnetism lectures. They are induced currents when you have a time-varying field. And of course, they cause you different kind of losses. So we also spoke about separation of losses, and you saw this especially in the lecture of Vittorio. I just made a summary of all these losses, and we distinguish hysteresis losses, classical losses, and excess losses, where the classical losses were related to the eddy and the excess losses to the eddy currents, which are caused only by domain walls moving. What kind of soft magnetic materials exist and how are they used in applications? So we spoke about different kind of materials, iron and metallic compounds, iron silicon, of course, for the motors, soft ferrites we used for high frequency applications. And applications, of course, are very different from flux guided DC applications to flux concentrators, shieldings, and then there are several kind of RF applications as antennas and so on. How can soft magnetic materials be measured? So preferred, of course, is the flux closed method because we have a very big problem with the demagnetizing factor, as you saw in the last lecture. So it's often very difficult to determine correctly the demagnetizing factor. And in a flux closed method, this the measurement result, of course, is the best. For example, you can measure toroid. Then you have already in the material all the flux closed in, but that's not always possible. So there are other kind of methods that are standardized, for example, as the Epstein frame. Okay, let's move on. Let's move to the second category. I already, of course, mentioned in the last lecture, there are not only two categories. The third category would be the materials that are used for magnetic recording, which are something in between these soft and hard magnetic materials. But today we concentrate on the hard magnetic materials. And when we speak about hard materials, then immediately we have to mention one thing, because you will see very often these different kind of curves, so pH and MH curves. Of course, one thing that always we want in a hard magnetic material is a high coercivity, and as we said already several times. So high coercivity is, of course, one ingredient very important, but nevertheless, we also want a good remanence. So you can see here these first curves here, which are in this subgraph A, are the curves for an ideal permanent magnet. And you can see a very squared loop, especially in the M/H curve. And this is because, of course, we want the very high remanence. High remanence almost as high as possible, of course. And not only that, we want the remanence to be stable in a very large field range. So you can see here in the ideal magnet, of course, it does not change at all, and then it switches down immediately to the other remanent state. So, but what's the difference about these pH and MH curves? The remanence, you can see here, does not change at all. But coercivity, be careful, changes a lot. So you can see here, of course, the coercivity for the pH curve and the MH curve are very different, because for the MH curve, we require that M is equal to 0. For the pH curve, we require that P is equal to 0. And this would give you M equal to -H. So if you read in a catalog, for example, of a permanent magnet producer, the properties of these materials, then please be careful and do not mix up these numbers. So usually you might find these P/H curves. So somehow physicists are more attached to the M/H curve. Myself, I'm very much attached to the M/H curve. It's more easy for me to interpret it. But the engineers very often use the pH curves because it's more practical for them for the design of magnetic materials and when they are used in applications. As you can see, here's a remark I just put. We did not speak about all these pH and MH curves because in the softer magnetic materials lecture, because there it does almost not matter. As I told you, the applied field that we use for soft magnetic materials in order to reach saturation is very, very small with respect to M. And so in this case, we have practically that the magnetic induction is almost equal to the magnetization. Another thing that you can see in this slide is already to give you, to touch immediately the different kind of materials. No? Here we have in the subgraph B, we have, for example, neodymium iron boron magnet. This is grain oriented. And then we have, on the other hand, in C, an isotropic neodymium iron boron. So these are the materials which are most used nowadays. Neodymium iron boron. We see the differences between the different kind of magnetic materials in these lectures. Of course, immediately what you will see here in this subgraph D is that one of the most early magnets, which is alnico, this has a much smaller coercivity with respect to neodymium iron boron. So you can see it's really a relatively poor permanent magnet with respect to neodymium iron boron and the magnets that we use nowadays. Nevertheless, we will see that it's still used because it had other kind of advantages. But let's now move on to why we use hard magnets. And mainly, I told you, one of the applications is to use hard magnets as a field source. So, for example, we saw also in the electrical motors, there's always a hard magnet inside, which acts as a field source. When we speak about field sources, then we also should speak about magnetic circuits. So here, for example, you have a plot of a magnetic circuit where the magnetic material is used as a field source, and then it's transported by an ideal soft magnetic material to the region where you want to exploit this magnetic field produced by the hard magnet. And here is plotted a gap between this soft magnetic yoke. So one thing that we assume, of course, that the soft magnetic material will guide perfectly your magnetic field from the hard magnet to the gap. And in this way, we assume that the permeability is very, very large, going to infinite, and the field of the soft magnetic material will not contribute. So what is the field we obtain given a certain hard magnetic material? This we want to know. And let's look at this magnetic circuit, and we use the Maxwell-EMPIR law and the theorem of Stokes. Of course, we consider here that we don't have any electrical currents involved in the production of the magnetic field. So then we can divide into these three areas: the area of the magnetic material, the area of the soft magnetic material, and the area of the gap. The area of the soft magnetic material, of course, is 0, due to our assumption. And in this way, we find immediately that the field in the gap is equal to the minus field in the magnetic material times a factor that is considering the length of the magnetic path. So we see immediately that, of course, this depends very much on the gap. No? The field that we can produce in the gap is the stronger, the smaller is the gap. And this, of course, is something that most of you will know. If you bring the poles also in an electromagnet, let's say, where you produce the field with currents very close, then you will have a higher magnetic field. Now let's use another Maxwell equation. Divergence of B is equal to 0. And we use the Gauss theorem. And here we have to consider the yoke cross section. So we find immediately that if SM is the yoke cross section in the hard magnetic material and SG the cross section of the gap, let's say, then we find this simple relation here. Now we can also consider the relation that we obtained before. If we use it, we find a relation between BM, so the magnetic induction, and the field HM. And you see here, this is a line with a negative slope, and you have a geometrical factor considering the length of the magnetic path and the cross section of the magnetic path. So this is an important relation. And in this way, we can find the field in the gap, depending, of course, on Jm, so basically the magnetization of the hard magnetic material and the geometrical factor, and of course also the field in the material if you're interested in. So going back to this relation, which we'll see in the next slide, is very important. This is a line. I told you it's a line with a negative slope. It depends only on the geometrical factor between this the cross section of the hard magnetic material and the gap. Then, of course, if we want to be a little bit more accurate, then we would have to consider also some losses that will happen on the edges of this circuit, for example. This is not a toroid, so the flux will not be closed in completely. So you would have to add this loss factor, which depends on the flux leakage that you might have. So let's give a closer look to this load line. Why are we interested in the load line? And we go back to this plot hysteresis curve of an ideal hard magnetic material. And look at the fourth quadrant. So let's plot this fourth quadrant a little bit better. We plot also this line. And of course, we know that the slope is decreasing with increasing gap. So I plotted here 3 lines with increasing LG. And then you have a crossing point here with your hysteresis curve. And this is exactly the point where you're working in your application. So this is the working point, let's say. And this depends basically I told you on this geometrical factor, but this geometrical factor, of course, is related to the demagnetizing field in general. So in general, you don't work in an application exactly in the remanence point. You work in a point close to the remanence. And this depends on how you designed your magnetic circuit. So you have to be very careful when you design your magnetic circuit. So not only the choice of material is important, but also the design of the magnetic circuit, as I told you. Another thing that we have to consider when we want to design this magnetic circuit and the application where we use our hard magnetic material as a field source, then we have to consider the energy product. So the energy product, I guess you studied already a lot in the lectures, especially of Vittoria, and you know that the energy stored in a hard magnet we can describe, of course, by this product B times H, where B is a function, of course, of H. And let's plot now this relation here. Now, here on this side, we have again the fourth gradient of our hysteresis curve. Now, in an ideal magnet, we have a straight line. And we can, of course, find immediately that this straight line will be related to certain parameters. So B will be the remanence and A is equal to mu0. So we can write immediately this product by expressing H, and you find this simple relation. This simple relation, of course, is a quadratic curve. And this is plotted here, this quadratic. So you see here BH plotted with respect to B on the right-hand side. Okay, if we want to know where's the point on this curve where we have the maximum, then we have to make a derivative of this BH with respect to B. This can be done very easily, of course, and you find that BH max is equal to 1 over mu0 JR squared divided by 4. So where is this point? Let's give a look. This is the characteristic value, of course, for the performance, for describing the performance of a hard magnet. And in this ideal magnet, we find it exactly here at B1/2. So this is the maximum value then that you can obtain. So this is an important material parameter. You will find this always in the descriptions of the magnet producers, this parameter, because this is really what you want to know if you're an engineer and you want to design your application needing a permanent magnet. But this is also related to our working point somehow. So let's give a look just before that, because if you go to a real magnet, then you might not have this perfect straight line. You will have a curve that is slightly distorted. And in this case, also your BH curve will be slightly distorted, and you will not be exactly at B1/2 with BH max. But the point is that with your load line, you would like always to work in the point where you have BH max. So you would like to have that your load line crosses exactly here in each situation. In your application, it might also happen that the situation is not that stable. You might have, I don't know, different temperatures, for example. The gap is slightly changing during the application and so on. And so this BH max will vary a little bit, and you want to adapt your load line and your working point exactly to the situation that you're actually having. If you can do that, which is not always possible, then we speak about a dynamic recoil. So one thing more to mention is, I already touched this briefly now, that it's not only in the magnetic circuit that you have to consider this fact when we have simply the geometric factor which is related to the cross section of the yoke, but also in a general situation we can relate it to the demagnetizing field. And you can see here in a neodymium iron boron magnet, for example, the different shapes now, how they influence your load line. So you have completely different load lines here. And in general, you can describe, of course, this by the demagnetizing factor. Hard magnets as a field source, here you can see several kind of arrays of hard magnets, which will give you different kind of magnetic material, magnetic fields. You can have uniform magnetic fields or non-uniform magnetic fields. For example, here you see a nice gradient field. Among the uniform, I would like to mention just the Bach cylinder, which is an array which gives you a very uniform field inside. This is kind of tube, which is cut in different pieces of hard magnetic material, and they are magnetized, as you can see here, in different directions. This is used very much when you cannot in your application use electrical currents, for example, for producing the magnetic field. You can imagine if you put outside another tube, then you can, rotating one tube against the other one, adjust this magnetic field. You can adjust as well as direction, as well as strength of the magnetic field. And so this is a very nice possibility to apply magnetic fields without using electrical currents. Here you can see a few applications of hard magnetic materials. And as I told you already at the beginning of these lectures, one of the most important ones are electrical motors. You can see here almost half of applications are electrical motors. Then another very big slice are actuators and loudspeakers. Again, a big slice, what we don't think usually are any kind of holdings. And then we have different kind of special applications. You can see MRI, or even oil dewaxing in pipelines, or separation as you need for recycling materials, for example, and so on. On the other hand, you can see here which kind of materials we use mostly. And more than half, you can see, are ferrites. I already mentioned to you are not the best hard magnetic materials, but nevertheless we use them a lot because they are very easy to produce, they are very stable, and they cost relatively little. Then, of course, the next slice is neodymium iron boron, very important hard magnetic material. It's performing much better than ferrites, hard magnetic ferrites. But of course, it's more expensive and has other kind of disadvantages. Then we have samarium cobalt alloys. We have aluminium nickel cobalt alloy. And in the other, we have mainly hard magnetic steels, which we will see then in the next slide. So I like this slide here very much, although it's a very old picture, also that one. You can see here the different sizes of different kind of magnetic materials that you need in order to obtain the same energy stored in the hard magnetic material. So this first one relates to the category of aluminium, nickel, cobalt magnets or hard magnetic steels, and then there are some kind out of other alloys very similar. performing similar, let's say, manganese-based ones, or cobalt platinum, and so on. So these are the 3D-based ferromagnetic alloys. Then we have ferrimagnetic oxides, which are basically barium ferrite and strontium ferrite. These are hexagonal materials, so they bring in magnetocrystalline anisotropy, and therefore they are hard magnetic. And then we have 3D4F intermetallics, which are neodymium iron boron and samarium cobalt alloys. And of course, from this picture, you can imagine already now, you see here we need 1 centimeter, here already a little bit more, and this is a huge piece. That this helped enormously to improve certain applications as motors or loudspeakers. No, you could not imagine to go jogging with loudspeakers of Alnico, very heavy ones, very big ones. No, nowadays we have these very tiny neodymium iron boron loudspeakers, headsets, and so on. Here again, you see the difference in sizes. This is nice, but you also see here the pH max of the different kind of materials that we have, and especially with respect to the time when these materials were developed. You can see the first hard magnetic materials, of course, performing really in a ridiculous way, let's say, with respect to neodymium iron boron nowadays, are hard magnetic steels. As I told you in the last lecture, steels are usually soft magnetic materials, but you can improve their hardness a little bit by creating some pinning of domain walls. So by introducing some defects, for example, at the grain boundaries and so on. The next material that was developed is Alnico. Alnico is also not that good, of course, as you can see here, as a hard magnetic material. Nevertheless, it has a very important advantage, as we will see in the slide. And then when the ferrites instead came up, also they, from pH max, they are not so good, but they have much better coercivity than Alnico, for example. Then there were a lot of studies on these ferrites. So this was, let's say, the first really important hard magnetic material that was developed. And this started, let's say, to be really important in the 60s, 50s, 60s, let's say. Then came up some iron cobalt materials. And then in the 90s, we have finally the neodymium iron boron materials. Okay, here you can see the main properties again of hard magnetic materials, and we see among them, of course, TRaMM, pH max, the factor that we needed to describe the working point. And another thing that still we have to consider is the Curie temperature. And this is exactly the reason why we still use Alnico in some applications, because you can see that Curie temperature with respect to ferrites, for example, is double. It's much, much higher. And it's as high as for samarium cobalt, for example. So if you have to go to high temperatures, then you might be forced to use a material which is not performing that well, but which resists to the high temperatures. Instead, for example, neodymium iron boron is among the materials which resist less to high temperatures. Here you can see again the plot of coercivity with respect to the applied field. And of course, samarium cobalt 5 is outstanding here in coercivity. Nevertheless, neodymium iron boron has a very nice hysteresis because it has a nice squared loop of hysteresis. When we speak about high coercivity, I said several times, then we don't have only to think about magnetocrystalline anisotropy, which will bring you in some coercivity, but also about microstructure. And this we see here briefly, because I mentioned this already several times. So if you have magnetocrystalline anisotropy, for example, now I showed you this example of cobalt once, that if you have a uniaxial anisotropy, then already you have a quite good magnetocrystalline anisotropy, as it happens in cobalt. But this gives you only an upper limit of your coercivity. We saw this in the Stoner-Wolfart model. So the best thing, according to the Stoner-Wolfart model, as I told you, would be to have a material, as is shown here, for example, that is composed only of single domain particles. If you have only single domain particles, then we can apply the Stoner-Wolfart model and we can reach almost the best value of coercivity. Nevertheless, on the other hand, if we have instead grains which are bigger, then you will have inside the grain a domain structure, as you can see on that side. And if you have a domain structure, then you have domain walls which move, and when they move with less energy. They require less energy, let's say, so they require lower fields usually. So this will, if you have very large grain, then you will reduce your coercivity strongly. So anisotropy, of course, is needed in order to have a good permanent magnet, but it must not be necessarily magnetocrystalline anisotropy. We very often speak about magnetocrystalline, although, of course, in the model of Stoner-Wolfart, also there we used a different kind of anisotropy. We used shape anisotropy. If you remember, we had this elongated ellipsoid. And here in Alnico, we exploit exactly this fact of shape anisotropy. So with a very tricky heat treatment in field, let's say, you can manage to have in this material needle-like nanoscale iron cobalt particles, which are in a nickel aluminium matrix. And you can see here along the field direction where we apply the field during the heat treatment, then you will have these needles in this direction aligned. And this gives you a very strong shape anisotropy in the annealing direction. And this is the perpendicular direction. As I told you already, the main advantage of this kind of material is that we have a very high thermal stability, but coercivity is relatively modest at 0.2 Tesla. In hexagonal ferrites, instead, we exploit exactly the magnetocrystalline anisotropy. So here you can see here this unit cell. It's a hexagonal unit cell, as the name says, and a uniaxial anisotropy in the long direction of the unit cell. So this material has a lot of advantages. You can see here low cost, corrosion resistance, it's easy to produce, and so on. But one of the main disadvantages is again the remanence that is relatively low. So we reach only a remanence of 0.4 Tesla. And this is due to the fact that here we speak about ferrimagnetism. So these are ferrites with a ferrimagnetism. We have 24 iron sites, 16 of them have spin up and 8 of them have spin down. So this gives you a total magnetic moment of the unit cell of 20 mu Bohr. And this is relatively low. And also for this reason, pH max is not the best one. One nice thing is that additional to the magnetocrystalline anisotropy, the material forms in these platelets, in these hexagonal platelets, and these have exactly the size, can be prepared in a way that they have exactly the size of single domain particle. And so we again in the Stoner-Wolfart case where we can have maximum coercivity. We can prepare them isotropic or anisotropic, both materials are used quite a lot. And then the third category, so the 4F3D alloys. So why do we introduce, of course, 4F elements? And this, again, we mentioned already in some of the lectures. So the main difference is that 4F elements bring in a spin-orbit coupling. And this strong spin-orbit coupling will bring you some magnetocrystalline anisotropy. For the 3D elements, we usually have more extended orbitals, as I already described to you, and they interact very much with the crystal field. So very often, the orbitals are not free to orient as they would do in an isolated ion, and they have to orient in special ways, and in this way, the orbital momentum will be quenched very often, is equal to 0. So we don't have LS coupling in the 3D materials, but we have strong crystal field splitting usually. In the 4F, it's the opposite. The 4F orbital is very much localized to the nucleus, so it will to the crystal field, but they will much more couple the spin magnetic moment with the L magnetic moment, and we have strong LS coupling in this case. Combining these two materials brings you the two advantages. We bring in high anisotropy and we bring in exchange interaction from the 3D element. And in this way, you can produce a very good permanent magnet. You can see as an example, samarium cobalt. I told you that this is one of the best with the highest coercivity, 2.2 Tesla. Is really an outstanding coercivity. The disadvantage of this samarium cobalt alloys is mainly that they are very, very expensive material because cobalt is very expensive. Cobalt is much more rare than any earth element, and therefore it's costly. But you can see here this really high uniaxial anisotropy of 17, 10 to the 6 Joule per cubic meter. Also, the second samarium cobalt alloy is samarium 2 cobalt 17. It has also a good uniaxial anisotropy, a good coercivity, and a constant remanence over a large T range. This is also very important for these materials. So samarium cobalt is also used a lot because it's stable in temperature. In these two kinds of materials, we have two different mechanisms which bring you in the high coercivity. You see this mainly here in this initial curve. So the first magnetization, let's say from 0 to saturation, which is very, very different for this kind of materials. And we distinguish these different behaviors in a nucleation type and a pinning type. So as I told you, for example, when domain walls move and they are pinned a lot, of course, this motion of domain walls, then you will have a flatter increase here, and you will reach a high coercivity, of course. But we can also have another mechanism which creates a high coercivity, and this is the nucleation of reversal domains. So if you think that you're coming from a fully magnetized material, and then you want to, you invert the field, so you try to nucleate reversal domains, then this can be energetically very, very costly. If this is very, very costly, then you will also reach a very high coercivity. So here, this is the distinction between these two types. Especially this spinning here in the samarium 2 cobalt 17 happens in the phases which are between the grains, so intergranular phases. And now neodymium iron boron, so this is the material that we use most because it's less expensive, of course, than samarium cobalt, and it's really very well performing. It has a very nice square loop and a high saturation magnetization. Here again, we have a strong uniaxial magnetocrystalline anisotropy. You can see here that the anisotropy constant is 4.9, 10 to the 6 joule per cubic meter. And of course, we have it along the long axis of this tetragonal unit cell. Again, here we have non-magnetic intergranular phases, which cause, additionally to this uniaxial magnetocrystalline anisotropy, a pinning of domain walls, and therefore we have a very high coercivity. It has as disadvantages a low TC, so you cannot use it at very, very high temperatures, because then MS, of course, will decrease very much. It's not corrosion resistant, and it's brittle. So if you ever played around with a neodymium iron boron magnets, you will see they break very easily. Okay, now we are already at the last part of this lecture. We go back to the measurement techniques. I already showed you all these kind of techniques the last time during the lecture. And what I mentioned very briefly was the torque method, but it's not a method, of course, which is used for soft magnetic materials. This is mainly used for studying the anisotropy in hard magnetic materials. And you can see here this setup. Of course, you suspend your sample, as I showed you already the last time, on a wire, and then it will feel a torque in a magnetic field, and you can measure this torque by reflecting light on a mirror which is attached to your sample. One of the problematics of this technique is that you need to have a single crystal. In a polycrystalline material, this method would not work. And then, of course, you always need very high fields to saturate your sample. So this is a general problem, of course, for the measurements of hard magnetic material. While soft magnetic material we can saturate very easily, hard magnetic materials, if you want to obtain a full hysteresis loop, then you always need very, very high fields. So this is was the last method among the force methods, which are based, of course, on the Faraday force. And then we said the flux method, which are based on the law of induction. And here already we spoke about these techniques. So one technique more to mention about the flux methods, or let's say, let's mention two techniques more. Thinking about also the problem to reach very, very high fields, because high fields, of course, you can reach with superconducting coils. This is one possibility that you can apply. But also there you need, this is a cryostatic method, so you need cold fluids, and of course the coils are more expensive than normal copper coils and so on. So let's say superconducting coils are more used for scientific purposes than for applications or engineering, let's say. And then another possibility, very nice possibility to reach high magnetic field is the pulsed field method. And you can combine this also with a hysteresis method. But let's give a look to the pulsed field method here. You can see here more or less the setup. It's very simple. You usually use only a coil of copper, which prepares your magnetic field. Of course, you have to use very, very high currents. You can see here you have to go up to several thousands of EMPIR to reach the fields that are required to saturate permanent magnets. And required, as I told you already several times, is, let's say, 3 times the coercivity of a hard magnetic material. For samarium cobalt, you would have to go up to 7 Tesla, for example. So then you need this 7,000 ampere, something like that, that you have to push through your copper coil. Of course, in order not to destroy this copper coil with your high currents and due to Joule heating, you need to apply it in a very brief pulse, and usually pulse of microseconds up to milliseconds are used. And you do this by discharging a capacitor bank. So this would be the electrical circuit that we use. You can also use this method to measure anisotropy, and that's also very nice, not only hysteresis curve, but also anisotropy. The other possibility is the hysteresis method in an electromagnet. So you clamp your magnetic material in the electromagnet. You use this maybe in combination with the pulsed field method. So for example, in our lab, we have both. You can see here, this is the picture of our electromagnet, which we use for also producing certifications of the hard magnetic materials. You maybe magnetize up to saturation with the pulsed field method first the material, and then you measure it in the with the hysteresis method. And this is performed usually at slow frequencies of a few seconds, and you can use pickup coils in order to measure the induced signal from your magnet. Here we are limited to 2.5 Tesla, which is more or less the limit, of course, of electromagnets due to the magnetization of iron of 2.5 Tesla. Then with the large coils that you have, you might go a little bit above, but this is more or less the limit of your method. Okay, now we are at the summary of hard magnetic materials. Here is everything that you should have learned in this lecture. We will look again to these questions. These might be questions that we will ask you after your examination, so think about. Now, these are the chapters that are used for preparing the lectures. And as I said at the beginning, so now there are some students connected. Maybe at the end of the lecture, after Vittoria's lecture, we can briefly speak about the examination topics, if you thought about that this weekend. And we can then also suggest you something. Okay, so that's all from my side. Do you have any questions?
Okay, so this is the second part of lecture 6, and so unit 6.2. In this second part, we deal with different classes of magnetic material that have, let's say, coupled effect, where we look at magnetism in connection with other effects. So, for example, stress and strain, so material that deform, and material that have certain thermal property. This kind of special magnetic materials goes under the name of magnetoelastic materials and magnetocaloric materials. Let's say, in a sense, these are referred to niche applications, so certain special application where you employ this coupling between stress and strain in solids and thermal property of solids. And we also try to, let's say, to mention a few possible applications with these kind of materials. As an introduction, I start from thermodynamic relation again. So this is a sort of a justification. Why do we have to expect in magnetic material some coupling between different degree of freedom, magnetic and structural and thermal? So we already mentioned the internal energy expression in thermodynamics, where we have not put all the terms, not coupling with all the possible fields. But now if we put the complete list, we see that the internal energy may change because we may have a heat flux. So TDS, temperature times the variation of the entropy. Or because we make an external an external action with the magnetic field, so mu0 HDM. But if we put also the mechanical works, then we have one term, which is the classical PDV. So pressure multiplied by the change of volume. And in general, the product of the stress multiplied by the strain. Again, if we express the thermal energy, we have all the change of energy with respect to the change of the extensive variable, the entropy, the magnetization, the volume, and the deformation, the strain epsilon. If instead we control the intensive variable, then we have to express this in terms of a Gibbs free energy. What happens is that nothing is against the idea that we have coupled effect. So if we make some magnetic work, then we get some volume change. And these are called the magneto-volume effects. Otherwise, similarly, we make some magnetic work and we get a strained material in certain direction. Or, again, we make magnetic work and we got a change in the entropy. So, connection magnetic and thermal. What is nice is that there exists a reciprocal relation. So, if we do have an action of the magnetic field on entropy, then it means that also temperature affects the magnetic part or the magnetization. And this is also true for the other cases. What we will do now is not to go into the theory, but to make a review of the materials, because these effects can be small or large, but it depends very much on the kind of material. So what we will make is a sort of a review where, let's say, we define the effect, and then we look at materials that have these effects large and can be possibly used in certain applications. So we start, we choose two classes, the magnetoelastic and the magnetocaloric effects. Let's start with the first, the magnetoelastic one. So as we have seen, one can couple the magnetism both with the volume and with the deformation in a certain direction, so with a strain. Therefore, when we talk about magnetoelastic effect, we have immediately to distinguish between what is called the volume magnetostriction and the anisotropic magnetostriction. These are two completely different effects. Let's start from the first, the volume magnetostriction. This is generally a small effect. So when you read about magnetostriction, in 99% of the cases, the study will refer to anisotropic magnetostriction. That is also the most used in application. But the volume magnetostriction is important in a very few but important cases. So what is volume magnetostriction? Well, if you take a magnetic material, then you will discover that there is a correlation between the volume and the magnetic order. And this you see very well if you take a magnetic material, for example, nickel, and you measure the thermal expansion coefficient. And you do this as a function of temperature. Well, the thermal expansion coefficient has the behavior from 0K to the Curie temperature which is shown here. If you take the full line, this is more or less what you can expect for solids in general. So you do expect that thermal expansion is positive. So when you increase temperature, the sample generally expands in volume. And you find that this thermal expansion coefficient is a monotonously increasing function of temperature. But if you take nickel, you will discover that there are some anomalies of this thermal expansion coefficient alpha. And this anomaly is very close to the Curie temperature. So at the Curie temperature, something strange occurs. In the specific case of nickel, you find that the thermal expansion coefficient has a peak, is a little bit larger than it would be most probably if the nickel would not be ferromagnetic. Then what you can do? You can, for example, let's say, take a theory or take a sort of interpolating line, which is a full line that is shown here, and take the difference. So how much more volume expansion you get because of only related to magnetism, only related to the fact that you are crossing the Curie point. If you're increasing temperature, you are passing from another state to a disordered paramagnetic state. The result is shown here at the bottom. This is just the integral over the curve above, not the full curve, but just the difference between the measured point and the full. This is the extra volume that you get because you have a transition from ferromagnetic order to paramagnetic state. As you see, from 0K to above Curie temperature, this change is very small. So it's around 0.12%. So in the full change of temperature. So not that large, something small. But there exists a correlation. So in the specific case of nickel, you will have that in the paramagnetic states, the cell itself will tend to be larger than in the ferromagnetic state. Well, it expands a little bit more because it also becomes disordered. And looking like this, it tells very little because, well, we may imagine that there can be a lot of anomalies in the thermal expansion of metals or whatever. But what is very interesting and really very relevant, that this is not always the case for magnetic materials. So not always you have the correlation between the paramagnetic state and the larger volume, but you can also have the opposite. And this is especially the case when you take alloys between iron and nickel. Take the case of this nickel-iron compound, which is iron 65, nickel 35. This is called EMPIR alloy. And by the way, it was discovered long ago, so at the end of the 19th century by a Swiss physicist. This EMPIR has a very special characteristic of behaving opposite with respect to the nickel. If you look at the thermal expansion, which is sketched at the left, then in EMPIR, you find that the specific volume tends to be larger when the system is ferromagnetic, is ordered. But then, if the cell tends to be influenced by the ferromagnetic state and then tend to be larger, this is in the opposite direction with the normal thermal expansion of materials. So it can possibly compensate. And this is exactly the case of the specific iron-nickel alloy. If you take different material with a series of composition between iron, that is this plot here with 0 nickel at the left and full nickel at the right, and you look at the thermal expansion coefficient at room temperature in this case, you find that at a certain point, this thermal expansion coefficient goes to zero, or very close to zero. This is very important for application because we have a material that, at least in the range of temperature close to the Curie temperature, in the case of iron and nickel, this composition, Curie temperature is going down, so close to room temperature, we have the compensation of the, let's say, usual thermal expansion mechanism with a volume magnetostriction that in this case is negative. So this EMPIR has been and probably is still really popular when you have to make very precise mechanical construction that is not changing volume with temperature, something which is very important in several cases. So this is the only example I want to mention, this EMPIR effect for the volume magnetostriction. And we can pass directly to the anisotropic magnetostriction, which is something that relates the direction of the magnetization with respect to the direction of the crystals, so the symmetries of the crystal. And say immediately one thing that, I mean, in a certain sense is very little known. We said that iron, nickel, the ferromagnetic materials have certain unit cell. So we said that iron is cubic and in particular is BCC, that nickel is cubic and is FCC. But this in the end, if we look at this into very much detail, is not true. Because if we consider also the magnetization in the cell itself, we discover that the cell is not exactly cubic. The size or the shape of the cell depends on the direction of the magnetization. So generally, if we do not apply any field, the magnetization will try to be, for example, for iron, along one of the easy axes. So in the language of crystal, it's a 1, 0, 0 axis. If we let the magnetization to be in one of the easy axes, we will find the cube is not really a cube. It's slightly deformed. It's slightly deformed in the case of iron, positively. So the direction, the axis, the 1, 0, 0 axis, where the magnetization is, and not the other two, will be slightly larger. Slightly, as you see at the right-hand side, is few parts per million, so something that is very small. How do we define this magnetostriction effect? We take the deformation and divide from some length. So the typical magnetostriction coefficients are these lambda coefficients. They're generally measured as part per million. And how much is this magnetostriction, or if it is positive or negative, it depends on many things. So in practice, people has taken single crystals of materials of iron, nickel, and cobalt, and I mean every kind, and has measured the magnetostriction by trying to align the magnetization with respect to the crystallographic direction and to measure the deformation. And what do you find? You find that in the case of iron, again, you have the easy axis along the axis of the cube. So the 1, 0, 0, which is the easy one. In that case, you find the lambda positive, 20 parts per million. So it's not really a cube, but is more tetragonal, let's say. But if you tend to magnetize along the R direction, then you will find that in that R direction, so along the diagonal, if you put the magnetization along the diagonal, and you need a large field to do that, then the deformation is on the other direction. That is, it contracts. The magnetostriction for the 111 R direction of iron is negative. Let's take nickel. nickel is FCC. So the magnetization will try to stand spontaneously along the 111 direction, the diagonal of the cube. That is the easy axis for nickel. If you measure the deformation with respect to the cube of nickel, you will find that magnetization is negative along the 111, exactly like iron. But in the case of nickel, the axis of the cube, 100, is hard. And if you try to put a magnetization there, you also find the magnetization negative. So they are both negative for nickel. Well, you imagine that now you can make this for every kind of crystals and so on. And discover that you may have deformations connected with the magnetization being in certain direction or other. How this changing? For example, if I take material that are used in practice. So, for example, take iron. Well, we know that we do not use iron, for example, in soft magnetic material, but we use very much iron silicon. We may also study iron aluminium, so an alloy that can be of interest and also easy to do. Then this magnetization coefficient will change. And look how, and they change in very strange ways. So this is something that one should know and measure very well. For example, if we take from iron, so we are here in this plot, we have the easy axis, which is here, with a positive magnetostriction, and the hard axis with a negative one. So let's follow what happens if you put silicon. Well, if we do not put too much silicon, it doesn't change that much. But then, if we increase silicon, you arrive at a certain point where both magnetostriction coefficients will tend to decrease. They do not go to zero at the same point, but there exists a composition where they are both very small. So, for example, if you put silicon 6.5%, you find iron silicon alloy where the magnetostriction is almost zero. You may ask why you care about magnetostriction. Well, for example, because you may consider that if you magnetize a piece of silicon iron 50 or 60 times per second, this magnetic friction may create problems, or for example, may create noise. So magnetic friction can be a problem for application in electrotechnics. So there exists a material where this magnetization coefficient goes to zero. And this is with quite large silicon, 6.5%. This is a material that has been prepared and produced in research labs. So, and it's a material that is generally prepared by rapid quenching, so not normal casting, and has been studied for a long time as a soft magnetic material with very good properties. If you take aluminium, everything is different. So, for example, if you look at magnetostriction coefficient along 100, you will find that instead of going down, it goes up. So iron aluminium is a material with quite large magnetostriction. Well, then let's forget for the moment about the noise effect, because we can also think of a material with a large magnetostriction as an actuator. We magnetize the material and it deforms. So we can also perform or transform magnetic work into mechanical work. Why not? So magnetostriction can be used in actuators. Iron aluminium is a material that could be possibly used. As you see, the magnetostriction is becoming quite large. But we have also to take care that not always we may have single crystals. So we have also to look at materials that are polycrystallines. And this complicates things very much. Because what happens if you take a material that is as a distribution of easy axis. Look at the plot at the right-hand side, the sketches. This is aimed to represent a material where you have several grains. So for simplicity, I've just put, I made it in 2D, and so I've put the grains, the crystals, as squares, and then I've selected by chance one of the direction as the local direction of the magnetization. This is a typical situation illustrating what you may have as a domain structure when you don't apply any field. So magnetization is close to zero, and the magnetization, and with respect to the local axis, local easy axis, it points in a random direction. Then we said, if you apply a field, the first thing that you do is to select domains. So have the domain wall motion and orient the domains, select the domain at the easy axis, which is most favorable to the direction of the field. So in the green dot here, I've just taken, imagine that I've put a field directed to the right-hand side. And then the domain I've just rotated of 90 degrees when needed, in order to take the easy axis, which is more close to the field. This process is quite easy, no? It occurs at quite low fields because you have only to move magnetic domains. Otherwise, if you apply a field extremely large, then you also overcome the anisotropy, the magnetic anisotropy, and then the magnetization will be completely aligned with respect to the field. But then, if we think about the magnetostriction, no, we've mentioned before, there are two different effects that occurs. So in the first, we aligned, we know that there is a deformation associated with the direction of the magnetization. But in the first, we just orient all the easy axes in one direction. In the second, we force the magnetization out of the easy axis. So you may imagine that the two magnetization coefficients, those with the easy axis, so the 1, 0, 0, and for example for iron, and the one along the diagonal, so the 1, 1, 1, they combine each other. What is the result? The result is that if you take a polycrystalline iron and not a single crystal, and you look at the deformation, so the strain as a function of the field, you find a puzzling effect. First, it is positive. So the first effect, or removing the domain wall and orienting the magnetization with the axis which is more favorable with respect to the field, generate a positive strain in the direction of the field. But then if you increase the field very much, the magnetization will try to rotate out of the easy axis. And for iron, as we know, the magnetostriction is negative. So we have a combination of the two. The result is that if you put a field that is very, very large, you got what is called the saturation magnetostriction. Saturation magnetostriction that has to do with polycrystalline material. So every time you see in publication, in papers or whatever, the value of the saturation magnetostriction, you need to know that this is related to the fact that you have considered polycrystalline material with grains oriented in any direction. So iron is quite puzzling in this sense. It's positive at low fields and negative at very large fields. Nickel, on the contrary, it has both the 100 and the 111 coefficient, both negative. Therefore, the combination of the two, it goes in the same direction. And we have that the saturation magnetostriction of nickel, polycrystalline, is negative. Cobalt is something in between, and you see they were shown there. So this is quite important because using polycrystalline material or using single crystal makes a lot of difference when we talk about magnetoelastic effect. So the crystal structure, the polycrystalline structure, orientation of the grain is extremely important. So once we have said this, we can, for example, look at materials that have a magnetostriction large, I mean, possibly larger than possible. Oh, this graph is not shown well. I don't see it. Do you see it? Do you see the graph at the right-hand side? Do you see the curves? Try to do... No, eh? So please, when you download the slides, check it, because I think that in the slides you could see it, or at least let's do like this. Let's do like this. Let's try to share the screen and see if we can have it there better, because I guess this is a mistake, a problem of the system. Okay, let me see if I can share the screen instead of using that. Let's take the slide and let's try to do like this. So I'm trying to share my screen so you won't see my face anymore, and put this slide. If someone, because I can, I cannot see the chat anymore. So if some of you has a microphone, please say something. Okay, we can see it. Okay, very good. So I go back because I couldn't see anything. So okay. Okay, so okay, let's stay here. One materials that have large effects. So again, very often the study is selecting alloys of different ferromagnetic material and studying the behavior as a function of composition. In this case, we have iron-cobalt alloys. Take the blue curve here, and this is the alloy of percentage of cobalt in iron. We already know the limits, because this is pure iron, this is pure cobalt. When we make the alloy of the two, we find that the magnetostriction coefficient becomes large. This is the saturation magnetostriction. You remember it was very small for iron, and it's -7. There are certain composition of iron cobalt when you reach this level here. If you then also alloy a little bit of vanadium inside, you find a material like this. Here you see the strain in micron strain, so it's part per million, as a function of magnetic field. 80 part per million with iron cobalt and a little bit of vanadium inside. Well, you see that now this material has definitely interesting strain, and you can use these iron cobalt alloys as an actuator. So from what I remember, I go back to the, yes, I try to stop sharing. Perfect. These iron cobalt alloys can be used for actuator for magnetostriction. What's the use essentially of this kind of material? Because the strain is very small, but they can make a relatively good force. So the stress produced by an actuator like this is reasonably interesting for application. So what else? Again, let's study the possible alloy of different material. Let's take the system iron and nickel. This system is extremely interesting. There are a lot of material used in application that are iron-nickel alloy. We already seen the EMPIR, which is a nickel 35, that is not very much interesting in terms of anisotropic magnetostriction, but it has the volume magnetostriction, really interesting, because we have this compensation of the thermal expansion. And then what happens to the magnetostriction coefficients? Well, the interesting is that we start from something of one sign with the iron and something of the other sign for the nickel. And also the anisotropy makes something strange, because we have easy axis 100 for iron and easy axis 111 for nickel. So when we make the binary system, we pass through a lot of different and interesting material. Regardless of magnetostriction, there is one composition when the anisotropy passes to 0. And this is called the region of the mu metal. These names, INVA, mu metal, permalloys, are commercial names. But very often you will find this in publication. But it's important to know the specific composition. So here, the mu metals are the compounds of iron and nickel where the K1 is equal to 0. So the anisotropy, you are really in between iron and nickel. These are extremely soft materials, very much used for shielding, for example, because they have a permeability very, very, very large. Another class of iron-nickel alloy which is very much used are called the permalloys. The permalloys are not 0 anisotropy, but they have the 2 magnetostriction coefficients that are very close to 0. And guess where it's very useful to have a very small magnetostriction? Where you don't want to have any influence from, well, we said already, no, that we may have an influence of the magnetic work on the deformation. So you magnetize and your system change shape. But we said also that we have the opposite. So if we strain the material, then we may have a magnetic action, and we will see this in the next. So we have anisotropy induced by the stress. If we have 0 magnetostriction, it also means that if we apply stresses, the material does not change its magnetic properties. So you do not induce anisotropy with the stress. And the typical situation where you will have stresses is the deposition of thin films on a substrate. So if you put a magnetic material in contact with a substrate, be sure that you will have enormous stresses imposed by the substrates. If you don't want your magnetic material to be dominated by the stresses, then you need to use a material with very close to 0 magnetostriction. Permalloys are materials that can be prepared as thin films, and their magnetic properties maintain their soft character regardless of the strains that are imposed by the substrate. This is an example. Let's go next. So, but what are the really nice magnetoelastic material? Because this is an issue that has been investigated a lot in the research on materials. And here I just mentioned 2 results of research of the last, let's say, 20 years and so, that are the record material. So most probably, if you find or if you have an application employing magnetostriction of magnetic material, you will have material of this kind. The the first is the so-called terphenol. Again, it is a commercial name of an alloy of terbium and iron. Terbium with a little bit of dysprosium sometimes. So we have no time to go into the details of this material, but what is interesting to see is the strain that you can get. Now you change your scale. You can almost get 0.1% of deformation, which is a lot. So more than 100 parts per million. What is interesting of this terphenol is that works well also under compressive stress. So really working again some stress applied. But the magnetic field that you have to apply, so look at the scale here, is quite large. So we talk about Teslas. So we need large field to induce these very large strains. Another class of material that is used or studied at least for this magnetoelastic effect are nickel manganese gallium alloy. Here I need to spend, at least in words, a few, to describe a bit what are these nickel manganese gallium. These are called the Oisler alloy. It's a special kind of crystals that exist not only magnetic, so nickel titanium, that exist as alloy with 3 elements generally, and they are cubic in one phase, and when they change phase, they become tetragonal. So these are the Oisler alloy. These certain Oisler alloy, they present this austenitic martensitic phase transition. So the austenite is cubic, but this martensite is tetragonal. The tetragonal phase is not unique. So when you are in the tetragonal phase, you may have what are called these twin boundaries. That is, the crystals produce a series of crystal domains, if you want, that are not equivalent in terms of crystallographies. In the special case of nickel manganese gallium, you have the coexistence of tetragonality and magnetism. And the magnetism is coupled with a certain easy axis. What does it mean? It means that if you apply a magnetic field, you select a certain easy axis with respect to another. But then here your easy axis is connected with certain one or the other of these twins, like in the picture shown there. So it happens that you can induce the phase transition between the twins just by applying a field. And the phase transition, you may imagine that it may induce a quite large strain. So again, here, look, we have the magnetic field in the picture below. You have the strain as a function of the magnetic field. And you will find that, again, you are around 0.1% of deformation, just because of the motion of these twin boundaries, is called. So nickel manganese gallium, these are magnetic alloys with so-called magnetic shape memory alloys, they are called, that undergo this phase transition between the twin boundaries induced by the magnetic field. So in a sense, they behave similarly to the shape memory like nickel titanium, even if they are magnetics. So you can drive them by the magnetic field. To conclude, let's say a few words on, let's say, an energy term that we have not considered in our micromagnetic theory, that has to do with magnetoelastic coupling. So if we magnetize a certain material, we have an effect of deforming the material. But what happens to the magnetic energy if we apply a stress? So we have said that all these effects related to thermodynamics, they always have reciprocal effect. So the reciprocal of magnetostriction, it's sometimes called stress-induced anisotropy. Every time you apply a stress on a material, you generate an additional magnetic easy axis that is associated with the magnetostriction. If the magnetostriction is positive, it means that tensile stresses generate an easy axis, a magnetic easy axis, in the same direction of the stress. But if, again, always magnetosuction is positive, a compressive stress generates the opposite. And this creates a nice way to generate anisotropy in a material. And this is also the main mechanism why amorphous material, they do have magnetic anisotropy. They do have magnetic anisotropy because in every point of the amorphous material, you may have quenched stresses because these material are never completely relieved by the internal tension. Internal tension are always there, ends are well seen by the magnetic anisotropy that are induced. So you may induce anisotropy by applying a stress, and this depends very much on the sign of magnetostriction, positive or negative. In this case, considering, for example, polycrystalline materials, here it's used the saturation magnetostriction. Okay, let's proceed. And let's stop here with magnetoelastic and consider magnetocaloric effects. Well, here we have the coupling between the magnetism and the heat, or at the entropy. Why do we have magnetocaloric effect? Well, the idea is the following, that if we consider the transition between the ferromagnetic phase, unordered, where the spins are all parallel, and the paramagnetic phase, we may have a change of entropy. We do have a change of entropy. We pass from order to disorder. Therefore, if we apply a magnetic field, we can change this entropy, this order, disorder. And so we have a change in the thermodynamic state. Well, as always, when we talk about a thermal effect, we have to subdivide into, or we have to specify the thermodynamic condition. So everything depends on what we do with entropy and temperature, or if we leave the sample isolated, or if we put it in contact with a thermal bath. Let's keep the temperature constant. We said if the magnetic field has an ordering effect, it means that if we start from here, a material which is not magnetized, and we apply a magnetic field, the entropy will decrease. So it will go down. It will correspond to less disorder, less entropy. If we do the same, but now we put in a condition when the system is isolated, now the entropy will be constant. Suppose we make an equilibrium transition, but the temperature will change. So applying a magnetic field to a magnetic material that is disorder means to increase the temperature. So when we apply a magnetic field, a magnetic material will increase the temperature. This is not very much interesting, but what is very much interesting is to start from an already magnetized material and decrease the field to zero, because then we cool it. And this has been demonstrated to be extremely important for generating cooling and refrigeration at certain temperature ranges where there is nothing to cool, where it's impossible to use any other method. This is called the adiabatic magnetization method. This is quite famous because it was, for a certain number of years, the record way to achieve cryogenic temperatures. What is the reason? So at the time, it was really difficult to go below the temperature, the liquefaction temperature of certain gases that were used. So researchers found that when they could reach the liquefaction of helium, they were not able to decrease any further, because any method which is used to cool, that is the expansion of the gas, compression expansion of the gas, you could not use it anymore because everything was liquid or solid even. So in a sense, physicists say there are no more degrees of freedom to act on concerning the molecules of a gas. But so the idea was that one could use magnetic materials, because it was already known that there are paramagnets that remains paramagnets till very, very, very low temperatures. And these paramagnets were salts, typically, made with certain magnetic elements like gadolinium, like manganese. So, for example, the elements that I put here, the compounds that I've put here, quite complicated compounds. So what happens to these compounds? They do not become ferromagnetic till very, very, very low temperature. So the idea of Jacques, essentially, and he got the Nobel Prize for this, was to use magnetic materials to go below the liquid temperature of helium. And he succeeded. The method was really successful. And the idea was really to use this magnetic material as cooling materials, cooling fluids. So in 33, they reached 0.25 Kelvin, then the millikelvin regime, and then the microkelvin regime. All this done, you see, long ago, and using magnetism. So the record at the beginning, many years ago, the record lowest temperature were reached by this adiabatic demagnetization technique, using this magnetocaloric effect of special material designed to work at that very, very low temperature. So the point is that the spins of these salts, they do not become ferromagnetic. So they do not force to interact. But then with the external field, you can make this transition between order and disorder and use their magnetocaloric effect to cool. Well, let's make a little bit of the theory here for those that are interested. How do we compute this magnetic entropy of a paramagnet? This is really interesting, and it's interesting because it tells us something interesting on the continuous, the use of classical vector and the use of quantum states for the spin. So it's easy to compute the magnetic entropy for a paramagnet, because in statistical mechanics, so this is a bit dedicated for those who know a bit of physics, you just sum up the partition function. That is, you make the statistics of these moments and you suppose them localized. But then you can do two things, and you have to do it in a field, in a magnetic field. So this field changes the energy. So you just want to compute how many are the states for these moments. And you can do in two different ways. By using a magnetic moment vector, which is a classical vector, or by using the spin or the magnetic moment in the quantum way. So you have to count the state by counting the possible discrete quantum levels. You can do both statistics, the classical one and the quantum one. And then you can compute the Gibbs free energy. So the same Gibbs free energy we were mentioning before, it can be computed thanks to statistical mechanics. And if you have the Gibbs free energy, we can compute the equation of state, that is the energy and magnetization. What happens? It happens that if you do this for the magnetization, you find these beautiful curves that already you've seen from Michaela. The magnetization curve of the classical vector is called the Langevin curve, very well known. So this is the magnetization of a paramagnet, where you have your local moment as a classical vector. And by the way, more or less, many paramagnets can be described by this Langevin curve. But if you take the discrete one, you get another curve, which is called the Brillouin one, where clearly the magnetization curve depends on the spin, or the total magnetic moment, if you like. What is very nice is that you do expect that the limit for a spin that is very large becomes equivalent to the classical one. So if you take the Brillouin curve instead for the spin 1/2, which is here, or spin 1 or spin 2, and so on, and you increase, and you find that the limit of the Brillouin curve for a very large spin is nothing else than the continuous one, the Langevin curve. So it looks very nice and convincing. But if you do the same for the entropy, this limit you cannot do anymore. So it tells us something very deep in physics, because it tells us that the description of the magnetic moment in the discrete is not sufficient to get the macroscopic picture. So you do not get any reasonable entropy with the classical magnetic moment. So you could already arrive to quantum mechanics only from thermodynamic reasoning. You don't need anything else. If you take the statistic of a classic vector, you arrive to unphysical behavior for the entropy. You do not have any reasonable entropy if you take the statistics of the continuum vector, of the classical vector. You need discrete states. Only with the discrete states, you reach what is reasonable for an entropy. That is an entropy that is going to zero when you align everything. Otherwise, the classical one, it doesn't go to zero. It continuously to become, undefined. This is very interesting for those who like physics. And also tells us that entropy, or the magnetocaloric effect at least, is very much related to the spin state, There has nothing to do. It has to do with the spin of the local moments. What are the largest spin or the largest J? This you find in the rare earths, because there, only in the rare earths, you find many electrons with spin not compensated. This is one of the tables that concern the formation of the spin states in the elements of the transition metal of the rare earths series, and it shows the spin, the angular momentum L, and the orbital angular momentum L, and the total angular momentum J. So, for example, gadolinium is the elements where the spin is maximum. You see here 7 electron spin non-compensated. But if we want to see the largest, or the element with the largest magnetic moment possible, at least in transition in the periodic table, this is holmium. That is the product of Gj times J equals to 10. Concerning magnetocaloric, it's the S that matters. So all this is the consequence of the application of the Hund's rule of quantum mechanics that Michael already mentioned. So gadolinium is a material with a lot of spin. No? You've seen also before that it could be one candidate for this magnetic refrigeration in cryogenic regime. Well, if you take this theory, so the maximum entropy change related to the spin, and you compare it with experimental material, you find that this is perfectly obeyed. So you really get the measured entropy change in these compounds using in cryogenics is really coherent with the spin 7.5 for the gadolinium. So quite successful in this sense. But what happens not in cryogenics? So if, for example, we want to use the principle in order to build refrigeration not in cryogenics, but in higher temperature, for example, room temperature, where we have to look for large magnetocaloric effects? Well, we have to look for this magnetocaloric effect close to the Curie temperatures, because it's there that we have the transition between order and disorder, and there, where we are close, I mean almost or a little bit almost there in the paramagnetic state, we have the ordering effect of the applied magnetic field. If you take nickel that has the transition temperature above 600 K, and you measure the magnetocaloric effect, you really find it. It's there, exactly like the gadolinium salts that we have shown before. The only problem that if you have 1 Kelvin of delta T at 1 Kelvin temperature, then it really matters. But if you have 1 Kelvin delta T at 600 Kelvin, it's almost negligible. So if we want to employ the magnetocaloric effect of ferromagnets to have any cooling effect at normal temperature, room temperature or above, it's really difficult, because this magnetic caloric adiabatic temperature change, they're small, they're generally small, not always small. By chance, gadolinium metal, one that has a quite large spin, 7.5, it also has the transition temperature very close to room temperature. So you can take the metal gadolinium as a possible working material with a magnetocaloric effect at room temperature. Take a magnetic field of 2 Tesla that is possible to generate with some problem, but not, I mean, even with permanent magnets or with an electromagnet, and apply the field, and you discover that you may have a temperature change of 6 Kelvin. 6 Kelvin is not that bad. It's already something. So why not to try to build up refrigeration by using these materials here? And this is the idea of this magnetic refrigeration at room temperature that is a working, let's say, it's a research topic where we also were involved. We were involved, especially in the past. So the idea is to make cooling machines exactly like you do for fluid, where you have a sequence of compression and expansion of a gas to do the magnetic field. So instead of, compression means that you take your material in a disorder state and you apply a magnetic field. So you will get a heating. And the expansion, it means that you take the ordered material and you remove the field. So you have disordering and cooling. The delta T could be small, but indeed, these magnetic refrigeration cycles, you can do it. You can really design. If you want to get a larger delta T, then the engineers have found ways to build up a gradient of temperature. So it's like to have many different cross-section of the material, not working directly with the butt and the hold butt, but working one with the other. And so you may increase this temperature change related to the magnetocaloric effect. And for example, in the picture here, you see a picture of one of these devices, prototypes, really working, where you get temperature change of 40 centigrade. You can make a home fridge with something like this. So again, well, what we want to see here is that if we have this coupling between the magnetic effect on thermal and the thermal effect on magnetic. And how can we state this? Through these Maxwell relations of thermodynamics. these are the relations that connect to each other. In this case, the connection is between the change of the entropy with the magnetic field and the change of magnetization with temperature. Now we understand why I said at the beginning, let's look for the magnetocaloric effect close to the Curie point. Curie point is where the magnetization changes with temperature quite rapidly. And then it means it is also the point where the entropy changes with the magnetic field. This Maxwell relation thermodynamics works very well because, for example, let's suppose we don't like to make thermal measurement and we are very good in making magnetic measurement. So let's measure the magnetization as a function of magnetic field at different temperatures. And let's try to compute the thermal effect directly from the magnetic measurement without using any thermometer, any calorimeter, anything. If we take this Maxwell relation of thermodynamics, it means that we can integrate the delta S as we do here and find that the variation of entropy is just the derivative with respect to temperature of this written there, which is the red region here. So the red region we can easily compute. We measure a lot of magnetization curve at different temperature. And then we compute all this integral. The entropy change will be nothing else than the derivative with respect to temperature of this integral that we can do, for example, numerically. If you don't believe it, try to measure the specific heat as a function of temperature and of magnetic field. But to do this, you have to be very good because you have to build the instrument yourself. They do not exist commercial calorimeters doing like that. But you can do it in your lab and you will spend a few years in developing that. Then you may have another way for deriving the entropy change directly from the heat. Then, if you like to compare, that is the result. For the gadolinium, a material that behaves in equilibrium, and that's the angles here you have computed with direct thermal measurement. The full black points are the ones deduced by the magnetic measurement, and they agree very well, very well. So this is a very good confirmation of the power of thermodynamics, also in making measurement. So instead of doing directly the thermal measurement, you use a magnetic method to derive a thermal quantity, which is the entropy change. Or then, if you like, anything, temperature change, and you can convert, possibly. Not all material, you can do this very easily because a few of these magnetocaloric material, they do have hysteresis, because also in this case, as we have shown for the nickel, manganese, gallium, there is a phase transition involved with the magnetization. Maybe this can move a little bit fast. And I mean, this is just a picture to show you what are the typical materials that are nowadays investigating for this magnetocaloric refrigeration. Let's see the time. Okay, just go through this cartoon because it shows exactly what happens if we have this second order transition where we pass from the paramagnetic state to ferromagnetic state through a continuous transition. This is the definition of second order transition. And what we have if we have a phase transition. So a magnetostructural transition where we do have hysteresis as a function of temperature, because not only we pass from order to disorder, but we pass from one phase to another phase. Okay, and this is just my last slide to show, comparison of one of the recent material, lanthanum iron silicon, and the gadolinium one. And with this, I can stop here and if you have question, please, you can ask it now. I think I can stop recording.